Hello, anyone. Good morning, Karen, as you are currently in the US. Thank you for accepting to give a keynote lecture in the 76th IIPF conference, and even more since it has turned into an online conference. I should say at this moment that for technical reasons, I am totally blind. I don't see anybody, I don't see anything, I don't hear anybody, and so I introduce the keynote lecture. Karen, I am very happy to have you here. As a researcher and as the director for the Future of Power Initiative of Resources for the Future, you play a prominent role in informing policies for the power sector in the United States and in bringing together industry experts and decision makers. For sure, a widespread decarbonization of the power sector and of the economy is needed to achieve a substantial reduction of US greenhouse gas emissions. One possible lever for this transformation is the flexibility of the electricity demand. This is exactly the topic of your present lecture, and we are looking forward to listening to you. Karen, the floor is yours.
Well, thank you so much, Maria. I really appreciate that. Thank you for the kind introduction, and thanks to you and the conference organizers for this opportunity, for the invitation and this opportunity to speak at this conference. I'm just really sorry that we can't all be together in Iceland, as I've never been there and I'd love to visit, but I'm looking forward to sharing these remarks with you today. So let me start by sharing my slides, and yes, we'll go from there. So as Marie mentioned, the topic of my talk today is going to be about the role of flexible demand in decarbonization, taking a perspective about policy, the role of prices, and automation. This talk draws on a couple of pieces of research that are actually in process now, and I've listed and want to thank all my co-authors on that work: Dallas Bertrand, Yishang Shi, Catherine Cleary, Casey Wichman, Josh Blantz, and Derek Wiedelman, and also acknowledge the Sloan Foundation, who's generously funded some of this work. So to start, oh no. My slides are not advancing. I don't know how to advance my slides. So hold on just a second. I'm sure we can figure this out. Yes, sorry about that. My own personal technical difficulties. Okay, so to begin with a little bit of background on the climate change imperative. So the Intergovernmental Panel on Climate Change has advised that, to get to controlling warming to where we need to substantially reduce CO2 emissions quite a bit by 2030 and a lot by the middle of the century, particularly if we want to stay below the 1.5 degree target, which now is greater focus because of the damages of higher degrees of warming. So, and we all know that energy use is kind of a major culprit here. So we're going to need big changes in the way we use electricity. As Maria mentioned, my talk is going to focus on the electricity sector, in particular, that part of energy use. And a couple of reasons for that. It's been the initial target for decarbonization policy. And that makes a lot of sense because there's a lot of cost-effective reductions, particularly in the US electric grid. But also, and more importantly, going forward, it's going to play a bigger role in the future. So when we think about deep decarbonization, there's many studies that look at what is going to be involved, but I think they all come back to sort of three key pillars. And one is greater reliance on energy efficiency and conservation of energy, the decarbonization of the electricity sector, and switching end uses to low carbon fuel supplies. So what that likely is going to mean in practice is that much of the activity that involves direct combustion of fossil fuels, transportation, heating and cooling, heating of buildings and other things is going to be eventually replaced by decarbonized electricity. And that's going to potentially more than double the share of electricity in final electricity consumption, according to this one study. All of this is going to have profound implications for how the electricity system and the associated markets will and should work. So what this talk is about is how the old way, managing electricity supply essentially to meet a parametric representation of demand, largely that, continuing to do that could impede decarbonization progress and raise the costs of consumers to getting to our decarbonization goals. So what's needed is a cost-effective way to reverse sort of the calculus here and bring electricity demand to supply. Key things that need to happen to make that shift occur include, number one, efficient time-varying electricity prices, something that economists have been asking for a long time, but that have a greater imperative now. In addition, to make those work effectively, we have to find ways to lower the costs of consumers engaging with those prices and with the sector. And that's going to include consumer acceptance of automation that could enable those lower costs. And also enabling clean energy storage in newly electrified devices, which in general, the things that we're looking at electrifying going forward in terms of implementing that third pillar of deep decarbonization all have this, to a certain degree, this energy storage capacity, and we're going to talk about that. So what I want to do is discuss a couple of research projects, again, that I have underway that are about engaging the demand side in these two different contexts, and sort of conclude with some thoughts on potential new models for the electricity sector that could capture some of these changes jointly. But let's begin with a little bit of background on the electricity sector. So again, apologies for this, but my talk sort of focuses on the US because that's the area I've studied the most. And what we've seen in the US is that in the past decade plus a few years, there's been a lot of reductions in greenhouse gases from the electricity sector. In fact, they've fallen by more than 30% since the middle of the early 2000s and the first decade of the 2000s. And the reasons for that are that natural gas, there's been technological developments that have made accessing natural gas cheaper and therefore low natural gas prices in the US. And so natural gas has beginning to substantially displace coal as a source of electricity. And also the cost of renewables have fallen due to technological innovations and also spurred by policies, including policies in Europe that have, where leadership has prevailed in terms of advancing renewables. So there's been declines, but in terms of getting from where we are to where we need to go, we're going to need additional policy. So this graph shows projections by the US Energy Information Administration in their most recent annual energy outlook of what the CO2 emissions look like going forward under a reference case and what happens with a series of different carbon fees. And what we see is that, okay, for a few more years, we have declines in emissions, but then they sort of flatten out if there's no additional policies. And carbon pricing can certainly help, and it could potentially yield big reductions. Now, the fee amounts that are labeled here are refer to initial fee values, and the policies that they model actually impose increasingly higher fees over time. These grow over time. The thing about carbon pricing is it faces a lot of political hurdles. Certainly true in the US today, and it's been true other places as well. So an alternative approach is something known as a clean energy standard. And what that is many of you may be familiar with renewable portfolio standards, which essentially require that a certain percentage, usually growing over time, of electricity that is sold to customers come from renewable sources. A clean energy standard is a broadening of that concept to include zero or very low carbon sources of electricity in that portfolio. So essentially, it's a way to keep existing nuclear plants in the mix, and perhaps even bring on new nuclear plants if that's something that a country wants to do, as well as, and if it's cost effective to do that, as well as potentially fossil generators with carbon capture in place, which captures a substantial amount. In this particular, so this graph shows, again, it's sort of a backwards comparison. In this particular study, they had a different baseline. But what we're looking at here is the mix of technologies used to generate and how that changes over time. On the right-hand side of the graph, under no new policy, and on the left-hand side, under a policy that essentially is a 90% clean energy standard by 2035 in the United States. And what you see here is that nuclear continues to supply power under this policy, and there's a couple of other renewable technologies that play a role, but substantial increases in wind and solar generation under this policy. So moving in that direction raises some challenges, and that's what is sort of leading to a lot of what we're going to talk about today. So what this graph shows, is the net demand minus renewable generation over the course of a day, representative day in March in California, and how that demand minus renewables, basically demand minus generation from solar, is changing over time as more solar generation is being added to the grid. And so because the solar is only available when the sun is out and it's strongest in terms of what it generates in the early afternoon hours, what you see is as more solar is added to the grid, the difference between demand and solar generation gets smaller and smaller as time passes. And you have what's essentially a challenge here associated with deploying all that renewable generation as more and more gets added, and you might not have enough demand. And also at the end of the day, when the sun goes down, you've got to have other generators available to come on. So this particular curve is referred to as the duck curve because it kind of looks like a duck. And the issue here is that these variable resources, solar and wind, don't necessarily and often don't track electricity demand very well. And there's big fluctuations in needs from other generators or other flexible resources that this puts a premium on. So to go along with this sort of graph about what's happening in terms of output, there's a parallel story about prices. And what that story is when renewable generation is abundant, it tends to depress electricity prices and therefore depress the marginal value of solar and wind. So you see here from a recent paper by Bushnell and Novin that in the middle of the day, adding an additional gigawatt hour of solar or wind just lowers the value of all solar and wind during those hours when it's abundant. And that's an issue. So what can we do to restore value to this high penetration of renewable electricity generation? Well, there's lots of strategies that are available because essentially we want to, make more demand be coincident with the availability of the resource. And the types of strategies could include things like grid scale storage, either with large batteries or packs of batteries, perhaps other technologies like pumped hydro, where you're kind of storing the hydro for use when the renewables disappear. You could also use transmission to link different regions where there's different demand profiles, different hours at the different time zones predictably, and also different renewable resources as well. So bigger geographic regions tend to have less of these issues of duck curves emerging. Both of these strategies are costly, although storage is getting cheaper. Transmission is particularly difficult in the US, not because of the cost of the hardware, but just the process of siting that new transmission. I think both of these things are going to proceed, but we're going to focus today on the demand side and finding ways to bring demand to supply. So essentially, we're talking here about reshaping that duck curve, bringing more demand to those low-cost hours and essentially absorbing the belly of the duck, flattening it up, and then doing so by bringing demand away from the high-cost hours when the renewable resources aren't available. So essentially, the standing duck becomes a flying duck, and it's flatter. So okay, what economists would recommend to do that, of course, is to use time varying prices. I mean, if electricity is really inexpensive during these renewable abundant hours, let's use prices to signal that. And even this idea that the cost of supplying electricity fluctuate over the course of the day or at different times of the year, but certainly over the course of the day, is not new. And it's certainly true with this increasing renewable penetration on the grid, but it's been true for a long time. But electricity prices that consumers pay rarely reflect these fluctuation actual costs over the course of the day. Typically, the prices that consumers pay are fixed. They might be increasing block, meaning that after an initial amount of necessary electricity is relatively cheap, and if you consume more than that, then you pay a higher price for the next block. But that's independent. That type of pricing structure is independent of when the electricity is used. There are some places, and we'll come back to one of those later in the talk, that have adopted time of use prices, and that's a pricing mechanism that declares in advance, well, typically these are the peak hours, so we're going to charge more during those hours, and typically these are the lower cost hours, so we'll charge less. So they provide some predictability about the time varying prices that wouldn't be there with real-time costs, but they capture a lot of the variation, albeit somewhat imperfectly. Another mechanism that's been used in a number of states is something known as critical peak pricing. This would, usually for customers who opt into this policy, this form of rate design, charge really high prices on the highest demand hours on particular days. So it happens in some places and has been used to the effect of trimming the need for peak generating resources. But efficient real-time pricing of the electricity that reflects wholesale price variations in real time is really rare. There's extensive economics literature that looks at the efficiency gains from real-time pricing, and I list a few of those here, and also critical peak pricing, which Josh Blantz, was one of my co-authors, has studied. For the most part, the savings from those programs, particularly the critical peak pricing, is the savings from a reduced need for adding peaking generating capacity to the grid. Okay, so why is there so little dynamic time varying pricing? Well, one reason is, and certainly has been historically, that meters that track electricity use by hour aren't universal. Now, there's a lot more of them out there, particularly in the US, but they don't apply everywhere. But even where they do exist, political support for these time varying prices is low. And it's in part true because electricity is largely a regulated industry in the US. And I think the regulators want to protect consumers from high prices during peak hours. And those high prices could be substantially higher. In the wake of the excessively high temperatures in California recently, you saw very high wholesale prices of electricity during peak hours, way larger than they typically are. And also, if making the shift is costly in terms of compensating the losers. And so that's one thing that keeps this from happening. And there's also the fact that consumers don't want to deal with having to monitor these prices and sort of following them and adjusting their demand when prices vary. So they really like advance notice. And that's one of the nice features about time of use pricing, is when the high prices are going to be in effect, so you can make decisions in advance. And there's just other things competing for consumer attention. So that's an issue. The orb here is something that some places have used to signal high price hours, but it's an issue for consumers. Okay, so these are the issues. Maybe there are some things that can help better align electricity consumption with the costs of generating that electricity. And those two things could be new technologies and electrification. So one, automation can help consumers respond to price fluctuations. There are devices out there now sort of help thanks to the Internet of Things that can kind of track electricity prices and help respond to those signals through software. And so I'm going to talk about some research that we've done at RFF that looks at smart thermostats and how effective they can be in responding to time varying pricing and help kind of move the needle on consumer responsiveness and therefore on acceptance of time varying pricing. And then a second aspect of electricity demand are these newly electrified loads. Things like electric vehicles, building heating and cooling, and water heaters, which is an example we're going to focus on, have a built-in energy storage capability, and that enables us to separate in time the electricity consumption needed to supply those services and the actual consumption of those services. So we're going to look at electric hot water heaters that optimize heating behavior and what opportunities those might bring. And we're going to do that by focusing on some recent research. So I'm going to start by talking about a paper that looks at smart thermostats and their interaction with time-varying pricing. So here, the idea again is that these low prices of electricity in renewable abundant hours should be good news for consumers. But consumers, as we mentioned, have kind of low price responsiveness, even when they see the prices, and that's because the cost of monitoring these price fluctuations can be high. So automation could help with both of those things, lowering those costs and kind of making the price responsiveness sort of happen automatically. But for that to work, consumers have to buy into letting that happen. And it's also important to understand if there are additional costs to consumers from doing that. So we're looking at a setting where consumers have smart thermostats. So it's not a matter of getting used to those smart thermostats. They have them, they've worked with them. But we're looking at the introduction of another form of automation that results in more price responsiveness. So the setting for this experiment, again, as I mentioned, there's not a lot of places that have real-time prices. There are some places that have time of use pricing. And this is an example of the Ontario time of use rates that are featured in our experiment. And so what the time of use optimization of the thermostat does is it allows for pre-cooling during those off-peak periods when prices are quite low. Here they're roughly half what they are during the peak hours, during the off-peak hours, and kind of lets the indoor temperatures float a little bit during the peak periods. The extent to which that temperature floats is a function of parameters that customers set. Of course, it's also a function of features of their house and other things. But what we're observing is when this feature is activated, this sort of linking of your time of use rate to your thermostat, so it can automatically respond. So we did this with an experiment, which was a great opportunity, and we worked with the folks that manufacture and sell the ecobee thermostats. And the questions we wanted to answer was, is this new service effective at shifting energy consumption within the day, lowering consumption, and how does it impact comfort levels within the home? And also with respect to consumer acceptance, how did consumers respond to this? So our approach to our experiment was a randomized encouragement design. We focused on Ontario because time of use pricing is sort of the default there, and most customers were under that. And we executed the experiment in the summer of 2019, joint with ecobee. So let me go directly to sort of our findings. All of the data we have comes from the thermostats. And so our proxy for energy use that we observe is the runtime of the air conditioning compressors. So basically, this is about shifting the operation of your air conditioner around in time. And what we see in terms of responsiveness to these rates is what we're hoping to see is that there is a little bit of pre-cooling during the off-peak hours, which are all before 7 a.m. And then really the large decreases in operation of these encouraged thermostats during the peak hours, and then a little bit of a catch-up effect later in the day. So that's what happens in terms of energy use, but there's also, in terms of thinking about the welfare impacts of this program for the consumers that are involved, it's important to understand how their experience of their air conditioner is also affected by this. So we developed a measure that we call our discomfort variable. It's measured in discomfort degree minutes, and it's deviations from preferred temperatures, in terms of that difference times the number of minutes in which those were experienced. So this degree discomfort minutes is like cooling degree days, for those of you who are familiar with that concept. And we see here that the majority of this discomfort that occurs is during the peak hours of the day, and that, the thermostats don't work perfectly, and the systems don't work perfectly. So everybody experienced some deviations from preferred temperatures, but we see higher discomfort in the treated group than in the control group. But then when we dig down a little bit deeper on that and divide our customers up in terms of how much time they spend at home, the various customers who were tapped in our experiment, we see that the folks who are often home, well, they have savings, and they also have discomfort effects here that noticeably during the peak hours. But the other groups of customers, those who are home less often, sometimes home, and those who are really not home very often, they see energy savings, and they don't really experience discomfort, in part because they're not home a lot. So when thinking about these results, we translated our compressor runtimes into energy based on some assumptions, and we do see some implications for electricity use. So there is a 7% reduction in electricity use during peak hours, overall a 2% reduction in electricity use, and a 1% reduction in electricity bills from this. So it's not big, but it is something. And importantly, what we find is in terms of the acceptance of automation, we looked at whether consumers were going with the settings that they initialized at the beginning of the program and how they were responding with respect to experience. And we find that basically the consumers in our experiment are willing to sacrifice control to the thermostat. And that, you know, the discomfort costs are really only borne by one particular group of consumers. So there's some promise here that automation might play a bigger role in the future in matching demand to supply. The second piece of research that I want to mention here is our work on optimizing electric water heaters. So it's about electrifying water heating and optimizing the operation of those water heaters and what we can gain from that, society and consumers. So a little bit of background on water heating. According to the Residential Energy Consumption Survey in the US, about 48% of residential water heaters use natural gas and 46% use electricity. So it's roughly half. Those natural gas water heaters do contribute a small amount of US CO2 emissions. And currently, water heating is responsible for 9% of residential electricity use, but that would increase substantially if everybody was using electricity for water heating. The thing to know about this is, but whether it's an electric or a gas water heater, conventionally the way they work is they heat, you know, sort of superheat your water tank and then turn off until your tank kind of drifts down either through use or just sitting there and not being heated to a low temperature that triggers the heater to come back on again. So it's a fairly parametric way of operating, and it's not optimal in any sense. So, but what if you electrified water heaters and they could respond to renewable energy supply? Then they'd essentially be storing this clean energy that's created during those abundant hours. And what we do in our exercise here, which is a modeling exercise, is take temporal demand for hot water heating services as given, and then see how water heaters can shift electricity use that would enable it to reduce the direct greenhouse gas emissions from heating water with gas and also reduce the greenhouse gas emissions relative to conventional water heating with electricity. So there have been some other studies that look at this, and one study actually finds that operating water heaters in this way is more cost effective than lithium-ion batteries if you're looking to back up your home solar system. So in that context. So in this research that I'm going to talk about, we explored a number of different questions, including whether these grid-connected water heaters could save money relative to heating water with natural gas, and whether optimization does a better job, can save money relative to conventional electric water heating operation, what sort of pricing regimes would be necessary for this to happen, as well as the potential greenhouse gas benefits, and a little bit about what the barriers are that need to be overcome to introduce these sources. So I'm not going to go into this slide in detail, except to point out that we got a model from DOE of hot water use that focuses on 5 separate uses of hot water in the house in 5 different sizes of houses in 3 different settings. So 3 cities in the US, Houston, Sacramento, and Chicago. And temperature plays a role in the efficiency of heating water. And so those are kind of different climate zones. And also they also have different electricity grids that are being impacted. So to give a sense of what we're talking about here in terms of optimal operation, this graph looks at the 24 hours of a day in the city of Sacramento for a 3-bedroom house, how the water heater operates under 3 different regimes. And the bottom half of the graph shows the variation in day-ahead market prices for energy in that particular location on this day. So if you just let the water heater operate traditionally, that's the gray bottom line, then that shows sort of the electricity use is kind of just, down and up, and it's showing the temperature in the water heater, which is reflective of when the heating occurs and when it's not occurring. But the other 2 lines, the red line, show 2 different of optimization, and they're subject to 2 different sort of constraints. The energy deficit constraint is essentially a constraint that says I'm not going to have any more failures in my attempts to take hot showers than I would under the gray line. And the red constraint actually says the temperature in my hot water heater can never go below what it would under traditional operation. And so it's important to point out that in this work, whereas in the work on thermostats, we couldn't really control comfort in the home. In this modeling, we're controlling the comfort associated with your operation of your water heater. So it's better or the same under optimization as it would be under regular operation, all again with an electric hot water heater. And so what this graph is showing is how the results with respect to savings of optimal operation of the electric water heater versus just regular operation vary across locations. And the reason they vary across locations is because of the variation in electricity prices. So the thing to point out is the biggest savings are in Sacramento, and that's a region that's being more impacted by the presence of solar power. And so the opportunities there are probably greater than in these other regions for this type of savings. So, of course, the other case to be made here is the case about switching from gas to electricity. And so here we evaluate sort of in an annualized basis the costs of water heating with 2 different technologies going forward. So it incorporates both the cost of the energy, the commodity cost of the energy, as well as the capital cost of the new hot water heater. So a new gas hot water heater actually turns out to be more expensive than a new electric hot water heater, but the electric hot water heater is more expensive to operate. So one of the key decision points here is what is the environmental impact of these 2 different approaches. That's going to influence the decision from society's perspective about whether or not this is a good switch. And we do see here we're able to capture in our model the emissions costs, using a measure of the social cost of carbon from the Obama era study about that. The social costs of emissions associated with gas. Of course, the social costs of emissions associated with electricity are going to importantly vary by time of day and by location. And so those are some things that we're working on in the ongoing part of this research, is to get a better sense of how those costs vary as well. But we can say a little bit about that. I mean, what this slide is showing basically is what those costs could be as high as. So they could be this high and you'd still be indifferent between making the switch as a societal choice. This graph is just illustrating sort of how, kind of going along with the duck curve we saw earlier, how emission factors vary by hour of the day. The data I was able to get here is average emission factors. Really what we want for our analysis is marginal emission factors, and we have a separate data source for that. But what I'm pointing out here is over time, as more renewables have come on the grid, these emission factors are going down, and they're going down more during renewable abundant hours, and they'd be going down even more during those hours. Yes, during the if this graph were focused on marginal emission rates, you'd see even bigger fluctuations during the day. And there's also changes over time, over the course of the year as well. Another lesson I think from this graph is that a lot of economic studies have looked at the emissions impacts of electrifying vehicles and other things, and they kind of focus on the current grid, but really the electric grid is changing. It's changing because of economics. It will continue to change because of policy. So doing an analysis using current emission rates, even though that's what we're doing, is going to be an incomplete picture of what's going to happen in the future. So what this graph really shows is what we saw previously for for California that the emission rates are going down. And what we've also seen earlier in this presentation for the US is also true in all of the states that we look at here. California, because of the composition of its grid being relatively clean, already has the lowest average emission rates of the 3 locations that we looked at in our study, but they're all coming down, and that's important to keep in mind for an evaluation of a new policy like this. So all of the numbers I've presented to you so far focus sort of on the cost of the energy commodity, the gas or the electricity, and we see that really the greatest opportunity from a consumer perspective to incentivize electrification is when the price that you're paying for the electricity is largely a wholesale price, but really when you pay for electricity, you pay retail prices, and that includes administrative costs and the sunk fixed costs of transmission and distribution. So as we electrify and add new sources of electric demand, that will have some impact on the grid costs through need to invest to deliver more electricity to customers, and also potential congestion on the distribution grid. We would assert that those are likely to be modest relative to the other costs that we're looking at. And indeed, it could be such that if you sort of offset that with the enabling of renewables integration that happens through these, that you could say that the grid costs are really negative in a sense. So that remains something for exploration. But when thinking about rate design, you have to think about recovering this fixed cost. And of course, the Ramsey rule would say that placing recovery on the inelastic demand, which would be largely, sort of the incumbent energy uses, one might say, then those might be responsible for sunk costs. And there really isn't a fairness criterion to guide this. So if we want to electrify, it might be time to think about charging different rates for those newly electrified loads, and sort of take this head on and think hard about what those costs might be. So so those are kind of the two experiments that we looked at. And there's some promising opportunities there, I think, to go about this exercise of bringing demand to supply. And those kind of involve, to a certain extent, consumers getting more active or enabling more activity by consumers with automation and data analysis and software kind of playing a role. But maybe, the role of the consumer, the way this actually plays out kind of in the marketplace could be really different than the way it does today, where, consumers essentially buy electricity. So I want to kind of leave with this idea, and I should say that right before getting on to give this talk, one of my colleagues sent me a link to a service like this for charging cars, which is something known as Canoe in California, where you can essentially month by month rent an electric vehicle that has all sorts of great features, and it comes with free charging. So basically, the idea is, could there be a future for energy as a service? I mean, a lot of what we do in the economy, more sort of a service-based approach, and these control devices and data and software are going to be important for realizing the gains that we talked about with automation. And so should basically the management of all that be outsourced from the consumer? So consumers aren't really the ones, at least for those services, buying the electricity. The electricity is an intermediate good that powers the energy service, hot water, electric transport, et cetera. And consumers pay for what they value, which is the energy service that the electricity and the devices provide. And so energy as a service providers like this Canoe opportunity that this new entrant in the EV sector, not so new, but I guess they're going public soon. But that's just one example, provides, they charge for the energy service, rather than just the electricity. And in that case, it's both the charging and it's also the car. So this is actually happening now, and perhaps, you know, it remains to be seen to the extent to which consumers will participate and it will overcome other challenges. I think there's some important things to understand about this energy as a service thing, opportunity. And one thing that I didn't talk a lot about in this talk, which focused largely on demand for energy, is that there are other services that are involved in running the grid, sort of ancillary grid services. And the energy as a service company could provide, you know, it profits from sort of selling the service and making gains from shifting the electricity demand in time, sort of lowering that portion of the energy costs of operating the hot water heater or the vehicle. And it also could enable participation of these devices in wholesale markets. So, you know, there are ancillary services associated with running the grid, backup types of things that provide reserves to continued operation. And it might be that these energy as a service companies, part of their business model would be to make money by participating in those markets. Hard for consumers to do that. Could be possible for Ecobee thermostat to do that, in a sense, if they were exerting more control over your thermostat. And so their agreement with you vis-a-vis time of use pricing, optimizing relative to time of use pricing of energy, might also include the ability to vary the operation of your thermostat and therefore your air conditioner to help supply some of these ancillary services. So those are opportunities as well. So it could replace the operations of these devices, or it could even replace device ownership, as is happening with this Canoe model. So I guess the word there is to sort of stay tuned and see what happens in terms of how new energy services, particularly newly electrified energy services, end up being delivered to households. So in summary, let's sort of review the high points here. Achieving our long-term climate goals is going to require decarbonization of production and electrification of additional energy uses. That decarbonization is going to be met a lot by renewable sources, but integrating those with the grid is going to pose challenges in terms of matching demand and supply. And we think that automation and electrification can help facilitate this shifting and help facilitate responsiveness to electricity prices. But there's going to have to be some innovations in rate design and perhaps other regulatory reforms and new business models that are going to potentially be important steps in realizing those gains. So I guess Mireille is not going to be able to join. So I'm going to say now that I look forward to taking your questions, and I'm going to follow the directions here for making it possible for me to do that. So let me stop sharing and look at questions. So there's a question here about studies looking at economies of scale in water heating. I guess in Iceland, there's a lot of central heating, and they're using geothermal. Yeah, so a central heating system, yes. So that definitely there, if you had a bigger system that was being supplied by the grid, so centrally supplied water heating or centrally supplied space heating with electricity, certainly those could also be operated in a way, and I expect with a lot more potential impact on ability to absorb low-cost electricity. So I think that and those centrally operated strategies presumably avoid some of the issues associated with rate design that would impact decentralized users that pose a challenge in the U.S. because you've got sort of presumably some sort of centralized operator making that heating occur. So definitely, I think there are opportunities there as well. I think that the opportunities really come when the electricity is coming from the grid, though, because that's what you're storing. But you could certainly store any source of renewable energy that way, and probably much more easily, and certainly with bigger oomph in terms of absorbing renewable supply than for decentralized uses. So really, I invite any other questions that people might have to type them into the chat. So I'd be willing to address them. I do know that one question that I would expect potentially to get here is why not just price carbon? Like, why isn't that sufficient to make all these things happen in the long run, or at least solve some of the problem with respect to renewables? And I will say that one of the features of the policies that are going forward, and they go forward even in the presence of carbon pricing in most places, although depending upon the magnitude of a carbon price in a market, their role may be diminished if carbon pricing is quite high. But is that a clean energy standard or a renewable portfolio standard provides another source of value to renewable generators. And so when they enter and participate in wholesale markets, they're often willing to bid really low prices. And so that has an effect on their willingness to enter, even if the value is low in particular hours. So a new question about whether demand is high at the same time that these resources are available. And I guess, that really depends by location. Like, the need to move demand around over time really kind of depends. I do know that if carbon-friendly sources, yes, solar power is available a lot during the day, but in the US, peak hours typically are kind of at night or in the early evening. That's when electricity demand tends to peak. And so that's why we face these ramping issues in between times. So there can be operational issues then as well. To the extent that that they are aligning, then that you wouldn't see as much depression in terms of this duck curve as we see, because the need to realign demand in time is sort of a function of this. So another example would be offshore wind. So to the extent that offshore wind becomes economic and largely exploited, it turns out that the peak times for offshore wind tend to be often coincident with the evening peaks. I guess the other issue is that there are periods of demand that it's going to likely spike when the solar power goes away or when the wind power goes away. So you need to have some flexibility there, and that's what the inherent storage in some of these electrified sources provide, particularly in terms of supplying ancillary services. So yes, and the other thing, of course, about optimizing with respect to carbon use is that if you're doing that through pricing, then you do have to have a situation where, of course, the prices are being passed on to customers. So, okay, so another question asks about, we calculated a discomfort index for consumers under time varying pricing. Would it be possible to calculate willingness to pay for indoor temperature comfort? Yes, so that's another thing that we're exploring in our research project, which is still underway, is sort of trying to understand what those trade-offs look like. And yes, I think it very much would be possible to do that. Would be even better if we had more variation in time in terms of the prices. But yes, it's part of our research plan going forward. So I think it would be an important thing to learn about. I mean, one of the reasons that smart thermostats have been touted for consumers is because they can potentially lead to energy savings. But as we point out, the cost associated with that is changes in your experience of the temperatures inside your house. And so one of the nice things about our particular experiment is that we're able to capture both aspects of that, and better understanding sort of what that trade-off is would also help in terms of designing these programs in the future, which I think is an important part of getting consumers to accept automation through their thermostat or any other devices, understanding these trade-offs. So any other questions from folks? I'd be more than welcome to hear them. And if not, I guess I just want to say thank you, and happy to participate. So happy to participate in this conference, and there's many more sessions ahead, and looking forward to the other keynotes that are happening in the coming days. So thank you very much again to Mireille and the conference organizers, and thanks to all of you for joining for this talk.